Hi there. We're going to start digging into forces and how they act on objects. So this week we're going to be looking at forces act to change the motion of objects. Now, this week we are going to focus on just this part of that statement, forces and how they act on objects. Next week, we'll look deeper at the motion of objects. So as these forces act on objects, they are going to make them move in some way. Now, before we dive into what we're going to do with these forces, we must first ask ourselves, what is a force? So for our 8th grade understanding and our 8th grade usage of what we're going to do, this is going to be the definition we'll use of what a force is. A force is a push or a pull on an object. Now, we're going to study 4 forces, although there are more of them. We're going to be looking at gravity. The force of gravity, or the F of G, is the way that we're going to write that when we're working with these forces here in just a minute. And what is gravity, just so we know what we're talking about? Over here, we've defined the force of gravity as the pull of Earth towards its center. Okay? And that's always going to be drawn as a downward force. Okay? Next, is going to be the normal force. Now, this one might be very abstract or a very, I would say, new concept to you. But a normal force acts when two surfaces or two objects press against each other. This one can't press on this one without this one pressing against this one. If they come in contact and they're pressing, this one is pressing against the other one and holding it up, just as this one is holding it up. So the normal force acts when two objects are pressing on each other. And normal forces, for our use of this idea, the normal force is always going to act in the opposite direction of gravity. So normal force, for our usage, for our sake, the normal force acts against or in opposition to gravity. If gravity pulls, the normal force will push upward against gravity. And there are two other forces that are going to act opposite each other. This one here is the applied force. We're going to write that as F of A. And an applied force, for our understanding, is a person pushing or pulling an object. So the person is applying a force on an object by pushing or pulling to get it to change its motion or to get it to move at all. Now, when you have ever tried to push or pull something, unless it's on the ice, there's been some resistance at first to get that thing to move. Well, that is our 4th force, or the force of friction, the F of F. And friction acts when two surfaces rub against each other. Friction is greatly reduced when you're on the ice, but when you're not on ice, friction is there. So friction depends on the surfaces that are rubbing against each other. Are they very rough surfaces? A lot of friction. Are they very smooth surfaces? Not as much friction. Okay, so these are the forces we're going to be working with. Now, one challenge is, well, we can't see forces. We can really only see their effects. But we need to understand how these forces work, because we live on a planet where all these forces are happening pretty much all the time. So how do we see forces? Well, we start by looking at an action or looking at an object and trying to assign to what's going on which forces are working on that object or acting on that object. And we do that by drawing something called a force diagram. Now, what are force diagrams? Well, they are a picture or a representation of the strength, the direction, and the amount of forces acting on an object. And this is where we're going to do our practice. We're going to learn how to draw force diagrams, and we're going to be practicing this skill over and over. So let's try our very first force diagram. Now, as I just told you, a force diagram is a way to represent strength, direction, and the number of forces on an object. So as we've already also talked about, there are 4 forces that we're going to study. But in not every scenario will you see all 4 forces being used. So let's dive into how we're going to use arrows and how we're going to use these labels. Well, a force diagram shows the strength of a force. And here's how it does that. The strength or the magnitude of the force is indicated by how long or how short the arrow is drawn. So between these 2 arrows, this arrow indicates a stronger force. This arrow indicates a weaker force. These labels we are going to be able to click and drag as we're drawing our force diagram, because every arrow that you draw needs to be labeled with what force that is. And finally, arrows are drawn in a specific direction. Unless we're in some weird scenario, gravity doesn't work that way, right? Gravity is pulling down. So when we're talking about a force of gravity, we're going to use a downward arrow. So the direction that the arrows are pointing shows us which way these arrows or these forces are acting on an object. So let's try a scenario. Here's the first. A book is resting on the floor. Draw all the forces acting on the book. Okay? So our force diagrams are going to be focused on one object. So that makes things a little simpler. Now, in order to make things even more simple, every object that becomes the subject of our force diagram is going to be drawn as a rectangle or a square. If we're talking about, draw all the forces acting on a bicycle, we're not going to take the time to draw a bicycle. We're just going to draw a square or a rectangle here, and then boom, we're off and running. So a book is resting on the floor. Here's the book. Here's the floor. What forces are acting on the book? Well, it's resting on the floor, and unless this tells us otherwise, we're on planet Earth. So Earth is always pulling towards its center. So the most obvious answer here, at least part of the answer, is the force of gravity pulling down. Now, I've indicated it by an arrow, but I'm not done with it. I need to come over here and grab the right label, F of G, force of gravity, and drag it next to the arrow. Now, am I done? Is gravity the only force acting on this object? Well, let's go back and do a quick look at all 4 of our forces and see if we can come up with this answer. We've got gravity. Is there friction? Is there a normal force? Is there an applied force? Let's go back and take a look. Well, this says that nothing else is happening to the book. You're not trying to push it or pull it, so there's no applied force. And the force of friction always opposes an applied force. So if there's no force being applied to the book by a person, then there's no friction acting against that applied force. So right now, we're not really worried about friction so much. But what was that one force that we said does oppose gravity? It's the normal force. If gravity is pulling down, which it is, the book should be right now hurtling towards the center of the earth. But it's not. The floor has stopped it. And the floor is providing an upward push force that is countering the Earth's gravity pull force and keeping that book at a constant speed, which is 0. It's not moving relative to the floor. So the normal force, or f of n is being acted on the book by the floor. So we're going to grab f of n, our label, and we're going to come and draw that next to our arrow. Now, we're done. A book is resting on the floor. Only 2 of our 4 forces are acting on this book. The force of gravity trying to pull the book down, and the normal force pushing the book up and holding it in place. If an arrow has an opposite arrow with the same length drawn on a force diagram, then we call this a balanced force. This length is the same as this length, and they are in opposite directions. So we would call this, and we would label this, a balanced force. Also, in a balanced force situation, the object's speed is constant. It is not speeding up or slowing down. You can think of it as neither one of these forces are winning or losing. They're kind of canceling each other out. In science, we call this having no net force. There is no net force. If we took this, subtract this, we get 0. There's no plus, there's no minus, there's 0. So both of these forces are canceling each other out, and we then say that this situation has no net force. The object's speed is remaining the same. But are there situations where the forces on an object are not balanced? Yep, there sure are. So on a force diagram, if any arrow does not have an arrow opposite it with the same length, then we call this an unbalanced force. This arrow is balanced by this opposite arrow. But this arrow doesn't have an arrow opposite it with the same length. This is unbalanced. And in this case, we then call this is a situation that has a net force. There's a winner and there's a loser. There is a net force in an unbalanced force situation. This means a force is actively changing the speed or the direction of this object. Now, this is a scenario where you can say or imagine that the box is being pulled or pushed on ice. And if there's a scenario that says on ice, we are letting that mean that there is no friction. So, this book is probably moving. Now, if there is a net force, we have to calculate it. We have to say, okay, yes, there is a net force. Well, how do we do that? We calculate the net force by comparing those 2 unequal opposite arrows. This one's balanced by this one, so those are balanced. However, we have an arrow over here and no arrow over there. We have to compare this arrow with what should be over here. Which arrow is longer? And by how much? Well, because the green arrow doesn't have an opposing arrow, we say that the net force is the length of that whole green arrow pointing to the right. And we have labeled what force is winning. So this whole green arrow in the right direction is the applied force. So the net force is this arrow, the whole thing, and we label what force that is. Now, what about maybe this situation? When there is an opposing arrow, but it is not the same length, it is shorter. How do we calculate the net force? Well, we compare these two, and we subtract this length from the longer arrow. And here's how we do that. We carefully, or as accurately as we can, kind of measure out how long this arrow is, and kind of swing it over here, and we cancel out this length of the green arrow. The net force then is the part of the green arrow that is left over after we subtract the amount of its opposition. So the net force then is the remaining length of this green arrow in that direction, and we label that force that is the winner. See, the magnitude of the applied force, or the strength of the applied force, is stronger than the friction that's trying to oppose it. So it is moving in that direction with that amount of force, and this is the name of that force. Now, gone carefully through this, because in the other part of the activity that you'll need to do, besides watch this video, is you're going to be given 5 scenarios that you then need to draw a force diagram for. So here's an example of one of these force diagrams that you'll be given on a Google Doc. And it's taking a second to load because, you know, #computers. So here's your first scenario, a book sitting on the floor. You are going to have a Google image like this, and you're going to get to draw your force diagram. And when you're done with the force diagram, you're going to type over here, is my force diagram balanced or unbalanced? Down here, you'll be able to type, is there a net force? Yes or no? If there is, in which direction, how much, and which force won? Now, how do you manipulate this drawing? It's a Google Doc, and Google Docs are very difficult to work with when it comes to inserting images. So I've drawn this image for you. You click the image and click Edit. Now, remember, the scenario is the book or the box, whichever that was, is sitting on the floor. Okay, so you get to come in here and grab an arrow and draw it on the object where you think it goes. That wasn't quite centered. There we go. Okay, grab an arrow, move it to where you think the force is acting. Now, don't forget, label every arrow. Hint, the labels that I have chosen are not right, and neither are some of the arrows. But I think you get the idea. When you're done drawing your own force diagram, hit save and close. And this will put your answer right there in scenario number 1. Now you just come up here and you're going to type, is the diagram that I've drawn, is that a balanced or unbalanced? I will type. And if it's unbalanced, you need to tell me what the net force is. Okay, and you will type that answer as well. So there's scenario number 2, scenario 3, scenario 4, scenario 5. Okay, do all 5 of these. If you have questions, email, or you can jump in on the virtual meetings. Now there's going to be another piece to our working with force diagrams, but that'll come in a few days. So be on the lookout for another lesson coming up here very soon. All right, so that's forces and the 4 forces we're going to study for a while and how to draw them on a force diagram. Don't forget, if you have questions, always reach out. Okay, good luck.